Welcome back, class. Today is still Monday, May 25th. Let's get back to our science. We talked about this song. We reviewed all our songs in the last video. We went through the new sound notes video. I just want to hit a couple things again, because if we were in my class right now, I'd be hitting them 6 or 7 times. So remember, sound, a couple of key things to take away, because there's so many vocabulary words. There's so many things to learn from this particular video section today. Sound needs matter to travel, right? Sound needs matter with vibrations. This is my matter, right? This is the thing that's vibrating off of it. If I have a bigger piece of matter, it's likely to create a slower sound wave. A slower sound wave is also called something that has a lower frequency. Frequency just means how fast or slow a wave is traveling with sound. So if I play a lower note, it usually has more matter or a thicker string to vibrate with and is moving slower. If I have a higher note, it is usually a thinner piece of matter or a shorter piece of matter, and that is going to create a faster sound wave moving back and forth really fast. So frequency is how fast it is, pitch is how high or low it is, and both of those are related to each other. High pitch, high frequency, low pitch, low frequency. The other thing we talked about is volume. A fancy way to say volume is amplitude, how big that sound wave is. So if I'm playing something really loud, I'm creating a really big sound wave. If I'm playing something really quiet, I'm creating a really small sound wave. So what does that look like with our Slinky model of a compression or longitudinal wave? So for example, this wave up top would be a high-pitched sound. How do I know? My Slinky is kind of more compressed together. It's moving faster. If I have a low-pitched sound, that's what this next one looks like. It's more spread apart. My sound wave is moving slower. If I had a loud sound, it would look like this Slinky down here because it's huge, right? It's got a big sound wave. And if I have a little tiny Slinky, that means it's quiet because it's a really short sound. So amplitude is the measure from the top to the bottom, and wavelength, or how fast it's going for frequency, is measured from the two crunched parts of the Slinky. Just fun extra information. So now we're going to do our lab. Our lab is I already went through all this, and it's making me go back through it again. Okay, we're doing the Screaming Cups lab today, and I just freaked my husband out by practicing this in my house. Our question today is, how will the different positions of our hands affect the sound from the cup? Hypothesis. I predict that when my hands are closer to the top of the cup, the pitch will be what? When my hands are lower down, the pitch will be what? Because. So let me show you the rig that we've got here. This is one I highly encourage you to do at home, especially if you have younger siblings who are bothering you when you're trying to do your schoolwork. This is a very annoying sound that it will create. So I have in the picture you use a plastic cup, like a plastic Solo cup works well. We're moving, so we hardly have anything left in my house at this point. So I used an empty coffee filter. Basically, you just want any plastic thing that you never want to use again. We're recycling. You also need a string. The string is better if it is yarn or wool or something like that. Or like twine that you might use. Just be very careful with twine that you don't hurt yourself. On the inside, you should tie a paper clip. I didn't have any paper clips, so I tied a bobby pin. So you basically need something metal tied to a string with a hole poked in the bottom, pulled tight. So then what we're going to do is we're going to take our fingers and we're going to slowly pull it down, and it's going to make a sound. I haven't wetted it yet, which is what really makes the sound. But this is my matter. This is what's creating the vibrations. It's echoing throughout here. At what distance down my string will my sound be the lowest? At which distance down my string will my sound be the highest? Will it be the shorter string, or it will be the longer string? That's really what I want you to keep in mind. So now let's fill in the type of data. Pause, fill in this section, and come back when you're ready. If you're listening to this video now, I'm assuming you're ready for the answers. The type of data we're collecting here is qualitative. We're not measuring a decibel. We're not measuring a frequency. We're just using words and our observations. It'll be pretty clear without collecting numbers. My independent variable is where my hand is positioned on the string, how long the string is. What's my dependent variable? What do I need to measure? My dependent variable that I'm looking for is how high or low the pitch is, depending on where my hand is down the string. Constants. What are some of the things I need to make the experiment fair? I need to have the exact same type of container no matter what I'm doing. I need to have the same bobby pin. I need to have the same string. I need to make sure my hands are equally wet each time I do this. You need to have water on the string because otherwise it won't work because of friction. So we are going to do, it's really hard to measure 0, 2, 4, and 6 centimeters. So we're just going to do all the way down, 3/4 of the way down, 1/4 of the way down, and like 1/10 of the way down, just to show the difference. Okay, so this is my bucket. Again, it would work better if I had a thinner piece of string. It would work better if I had a paper clip and a plastic cup, but we're improvising. This is COVID-19, so let's see what it sounds like all the way down first. So this would be our 6 centimeter measurement. Ready? 3, 2, 1. So notice that distance down here. Record observations on your sheet of what that sounds like. Okay, so now I'm going to go about 3/4 of the way down. Are you ready? This is what it sounds like. Record your observations. So we've now recorded for our 6 centimeters and our 4 centimeters. So make sure you go back and listen to those sounds again if you need to. This is the 2 centimeter sound measurement, like 1/4 of the way down. It's harder the further you go up. So write down your observations, and 0 centimeters, are you ready? Okay, so as you notice, the closer my hand is to the top, right? 0 centimeters almost doesn't have any sound because we need matter to vibrate in order to have any sound. So write your conclusion sentence while you're doing that. Just note this is the best way to annoy a sibling, dog, or husband in my case. Just keep this by your desk. Go away. I'm doing my homework. Are you annoyed yet? Great inventions of science. My dog is barking in the background because she doesn't like the noise. So what's pretty clear in our conclusion sentence is that the closer we are to the cup, with the exception of the 0 centimeters, the lower the pitch is. And that's because we have more matter to vibrate. It's the same thing when my hand is further down the cup as it is playing a low note on my guitar. Because it has more distance, more matter. My hand is closer to the top. That's like playing a shorter string or a skinnier string or a higher note on my guitar. So that's just kind of a way to practically use this information to create something very annoying. So now you need to draw what you think the sound wave would look like for each of the following distances based on their pitches and loudness. So I'm going to draw this with you. Draw what you think that 0 centimeter one would look like. There was very little to no sound, so I would draw a little teeny tiny one, but it is pretty high pitched. So your wave should look something like this. Really tiny because it's not very loud, it's pretty short, and pretty close together because it's a pretty high pitch. The next one, 2 centimeters, was a lot louder, and I would say they're all pretty consistently loud after that, but it's still a pretty high pitch. So it should look something like this. Still pretty close together, but much louder. Our next one is much lower, so it's still the same amount of loudness, but you should be able to see my compressions, my slinky is getting a little bit less squished together. And then finally for our low note, probably looks something like this, right? Really, really far spread apart. So you can copy my slinkies if you want to. These are compression waves. When they're shorter, like my 0 centimeters, that means they're quieter. When they're closer together, like my 0 and 2, that means they're higher pitch. When they're further and further apart, that means they're lower pitch. So you can do this with me at home. Give me a high frequency sound. This is high frequency sound. Give me a low frequency sound. This is a low frequency sound. High pitch, high frequency. Low pitch, low frequency. Compression wave sound energy. Give me a high amplitude sound. This is a high amplitude sound. Give me a low Loud means high amplitude. Quiet means low amplitude. Sound, energy, longitude. The key thing about sound energy waves is they go back and forth like this, right? When it leaves my mouth, it's going like this, almost out to my other matter in the room. If you could show a map showing the relationship, graph showing the relationship between pitch and distance down the string, what would it look like? Explain why, and what would the axis be labeled? This one is a think question. So let's think about this. My first graph, it shows an arrow going up, right? Something kind of like this. So let's think. As the string gets longer, as the string gets longer, does my pitch get higher? That one's not going to work, right? As my string gets longer, my pitch gets lower. So that one's not going to work. Let's take a look at our next one. My next one looks kind of like this, right? So this one would be, as my pitch is getting shorter, my sound is getting lower, which also doesn't make sense. The next one shows a weird arrow going this way. And so this one is showing me as my string is getting longer, my pitch is getting lower. No. It should be the one that looks like this, because as my string is getting longer, my pitch is getting lower. That's what I really meant to say. I apologize if that wasn't clear. This one, because as my string is getting longer, my pitch is getting lower. That's what I was trying to say the whole time. So make sure you keep that in mind as you're responding to this lovely question that I totally forgot the answer to as I started explaining it. Thank you so much for joining me today, guys. I hope you enjoyed our annoying lab. Go create your own annoying noisemakers for your siblings and family, and have a wonderful evening. Until Language Arts, when I'll see you again.